the fifth lecture of NSM online course on GPU programming with OpenACC. We looked at basic introduction to GPU, then basic OpenACC overall execution model. We were then looking at specific constructs like parallel kernels, and today we are going to look at the loop construct, which is a work distribution construct. So let's get started. So the overall loop construct is something which we have seen in one of the earliest examples, and it's a primary construct for work distribution. That means that if you have a lot of several iterations to be done or overall amount of work to be done, that can be distributed to across different threads. And this also means that different iterations of that loop are going to get distributed to different GPU threads. In general, this loop construct can be inside a parallel block, that is hash pragma ACC parallel, or it can be combined directly with parallel. So either way, it has the same effect. But in case you want to have, you want to do different kinds of clauses for different parts of the parallel loop, you might be able to use hash pragma ACC parallel as at one place, and then hash pragma loop with other constructs at a different place. Alternatively, you can combine them and just call it as hash pragma ACC parallel loop, and that will take care of parallelizing that loop. Okay. It can also support something called as declaration of private variables, because when we say that a particular processing inside the loop is going to get distributed across different threads, threads are going to access the data, and whether that data is shared, which is the default, or it should be private, that needs to be specified. So by default, the index variable, that is the, let's say for loop contains I as the index variable, I equal to 0, I less than n, I plus plus, then that I becomes private variable by default. But if there is any shared variable, for example, I am using sum in our example, then that by default remains as a shared variable. So if we have to specify that certain instructions, or certain variables should be private, thread local, then we have to declare those as private variables explicitly. And we'll also see towards the end of this class that the loops also supports something called as a reduction, which means a hierarchical computation, which is going to give us certain kinds of functionalities, right, which will help us in the context of when there is synchronization required across threads for certain kinds of applications, certain kinds of operations, not all. The overall syntax of the loop construct in case of C++ is hash pragma ACC loop, and then we specify different clauses followed by the for loop, and then that pragma is applied to the whole of the for loop. In Fortran, the do loop is what you will use. Yeah, so that is the basic syntax. Let's directly jump into one particular example, right? So we said that it could be inside that hash pragma ACC parallel, hash pragma ACC loop could be inside parallel, or it could be combined. So as an example, this is just an initialization of a vector with a of I equal to I, and that I can apply as ACC parallel and ACC loop, and that takes care of parallelizing this particular loop. So can somebody tell me what happens if I do not have hash pragma ACC loop? What happens in this example if I do not have hash pragma ACC loop? Any suggestions?
Maybe multiple threads execute the loop individually.
Right. So as Durbajyoti says, that hash pragma ACC parallel is applied to the block of the code. That block of code here is the for loop. And that means that that doesn't mean that the for loop is going to get executed in parallel and then the loops iterations are going to get distributed. It means that each thread is going to run one instance of this for loop. And this A of I is going to be by default shared, and therefore different threads will run this for loop, right? So if I mean, in this case, we have not specified number of gangs, but assuming that number of gangs is 10, there will be 10 into n number of iterations of this for loop, or 10 instances of this for loop, which are going to run in parallel. All of them are thankfully going to set the same values in A of I, so there won't be any problem. But that is not probably what you anticipated this to be, right? So to specify that you are interested in work distribution and you are not only interested in parallelization, you need to specify loop. Okay, so that is what this code achieves, and the same thing can be achieved by combining these two as hash pragma ACC parallel loop. Okay, any questions so far? Okay, so this is the basic syntax of hash pragma ACC parallel loop, and this we can apply to, well, the usual loops which allow you to distribute the work across different threads, and in this case work means n iterations. So n iterations get spread across multiple threads, very similar to what happens in case of OpenMP, for those of you who are aware of OpenMP already on the CPU. And thankfully, it also works with while loop, which means that even if you have, let's say, I equal to 0, and then there is a while loop, and just before while you have this hash pragma ACC parallel loop, thankfully, the OpenACC compiler identifies this correctly and performs the usual parallelization as exactly in the case of for loop.
So for this OpenMP, does that work for while loops in OpenMP? I'm not sure.
OpenMP, does that work for while loop? I'm not sure. I don't think so. I'm not sure though, but I don't think it works. Yeah, in case somebody knows, yeah, just says no. Yeah, I don't think, I think because the syntax also has hash pragma OMP parallel for, so I think it does expect that for loop to be.
Yeah, right. It has a for, true. Okay.
All right, sounds good. Let's move ahead from here. An obvious next thing to do once we have parallelized one loop is to try a nested loop. And many times, for example, in matrix computations, we have these nested loops for I and for j. So can we parallelize these? Well, you can, provided your compiler supports it, right? So depending upon the PGCC or PG Fortran version, nested parallelism, this kind of parallelism is called as nested parallelism. There is a loop for I, and then there is another loop for j, and it so happens that each thread which is working on the I iteration also has, also spawns multiple threads for the j loop, right? And therefore, if you think about the second level of threads, those are going to be n square in number, assuming that both I and j loops run for n iterations each. Unfortunately, in my machine, whenever I ran, this is not supported, and when I tried this particular code, I got this error. So in case you get this error, that means that your compiler also doesn't support it. But yeah, there may be some other compiler, another implementation of OpenACC. The one I have is NVIDIA HPC compiler. There might be other implementations which might support nested loops. In case you find that it is supported, do let me know. I will try that out. The idea behind nested loops is that sometimes you might, in general, you don't really require a nested loop. Why? Because you can achieve the same thing by, in some sense, combining these I and j loops, as I will show on the next slide. So this is not the end of the story. You will be able to do something about nested loops in case of even the current version of OpenACC that that we can execute our programs with. But the reason why you would require a nested loop, okay, let me ask you, why would you require a nested loop? Okay, Swapnil says GCC 11 also fails to compile while loop with compiler run through -f OpenACC parameter. For example, GCC -OpenACC loop example.c, if the program contains while, it errors out, however, nested loops are supported. Oh, great. Thanks for confirming that, Swapnil, that it supports nested loops, and it doesn't support some of the parts that we have seen, which is supported with OpenACC, for example, the while loop. Right? So in general, we need to, as I was mentioning, different, I mean, OpenACC has certain standard. All those standard functions need to be supported. Anything beyond that is in the hands of the compiler writer, I mean, the appropriate implementation. So it just happens that with respect to this NVIDIA HPC compiler, the while loop gets compiled, but that is definitely not something which is very important. You can always convert it into a for loop if you want to execute it. Swapnil says one reason we require nested loops is for matrix kind of operations, 2 or more dimensions. That is possible, but then isn't it possible that I might be able to run that with, let's say, n square threads, right? And then in some sense I unroll these loops and I run it. I mean, it's a rather more roundabout way of achieving this, but there is some very important reason why you would want to have nested parallelism. Can somebody think of that? I agree, matrix-based codes do require, it's a natural way of implementing using nested parallel loops, but there should be some important reason. What could that be? Kernel from kernel call from another kernel. Yes, but that is implementation aspect, Josh. So what is the application semantics which forces you to use nested parallel loops? Okay, so I'll probably extend my argument from Swapnil's argument. So I am able to convert this matrix operation from n nested within n to an n square at the outermost level in the more like unrolled case, because every I has n number of j iterations. But if that is not the case, the number of j iterations is dependent on some function of I, then having nested parallelism is going to be different from just unrolling the two loops. So what that means is that the j loop is not fixed now. It is dependent on some function of I. And this many times, I mean, one nice example is if you are going over a graph which is not stored as adjacency matrix, but maybe adjacency list. So the outer loop might go, I loop might go over the vertices. The j loop might go over the neighbors of each of that vertex, right? So neighbors of I. Now the neighbors of I in a graph can be arbitrarily different from 0 to n-1, and therefore the number of threads with which you need to launch the inner loop, the j loop, has to be different across different values of I. It's in some sense a function of I. And therefore you might require a nested parallelism over what is possible using an unrolled j loop, I and j loops. I hope that is clear, but yeah, we'll move ahead from here. If there are any questions, feel free to ask. All right, so yeah, so by default, what happens is that when you have this nested loops, I mean, it could be 2 loops, 3 loops, doesn't matter. But if you specify hash pragma ACC parallel loop outside, you are going to, I mean, the compiler is going to apply that parallelism only to the outermost loop. I mean, only to the loop which is just following that particular pragma, which seems reasonable, right? So in this case, that parallel loop is applied only to I and not to j, right? So this seems to be a reasonable thing to do. And -minfo Excel can give us that information. So please note what is the information that it is giving. And then but there is a way in which I can combine these, more like an unrolling of the j loop, which allows you to collapse I and j loops. If I unroll j loop, in some sense you are allowed to collapse I and j loops together, and there is then a single body of a of ij equal to iin plus jj, and these for I and for j get collapsed into some n square space. Okay, so that essentially is a collapse clause which allows you to combine these two loops together and parallelize singly. Parallelism is still at the outermost loop, but that outermost loop now is getting formed by 2 loops, both I as well as j. Instead of just parallelizing the I, you are parallelizing both ij together, and therefore you require n squared threads instead of n threads. So in the previous case, we had n threads without collapse, and now with collapse, I have n squared threads, or at least something proportional to n square, which are going to execute this a of ij equal to iin plus jj. How does, if you look at this particular part which gets collapsed, how does the output of the compiler change? It now says that I have this gang and vector, and that is getting collapsed into a single loop, right? So it's not generating two different outputs. In the previous case, it was generating loop gang separately and loop vector separately. Now it is not doing it that way. It is combining these two in some sense. So we have this n square space which is getting addressed directly with number of threads proportional to n square instead of number of threads proportional to n. Yashpal says, can we launch n square threads using single pragma and works the same way a nested loop can do? Just says, yes, we can do, but we need to change the loops accordingly. However, compiler does it automatically using collapse. Good. Yes, correct. So I can specify all these terms myself, and then the compiler will not interfere with that. So whatever, so compiler says that programmer is always correct, right? That is the behavior that we will see always. Programmer is always correct. So if programmer specifies something, compiler will not deviate from it. Okay? Unless there is some inconsistency which gets created, in which case the compiler is going to give some sort of an error that, boss, you have written two things which are not fitting together, so there is something wrong. So it will give a compile time error. But otherwise, it will assume whatever is given, right? That is the order of the program. Yeah, but you can launch n square threads and it can work in exactly the same manner as a nested loop, provided we write it as a single loop, right? So we can write a loop which is invoked with n square threads, but we'll have to write it as a single loop, just as a for I. That's it. There won't be any for I followed by for j. If there are two, then we have to use a collapse, so that compiler helps us do that automatically. There is also another thing. I mean, you can write it, but this is a more natural way of writing. All right. So, any questions on this part? Okay. So, nobody has asked me what is that 2, collapse 2. What could that be? So, let me ask you. What could that be? What is that collapse 2? What does collapse 1 do? What does collapse 0 do? Any suggestions on this one?
This 2 means you are collapsing the next 2 level of loops.
Right. So as Dubajyoti has rightly pointed out, and Rajan has also pointed out, it's collapsing. It's showing the number of levels which you are collapsing into one, and that should be 2. So this means that the default for collapse is collapse 1. If you don't specify, that means it is collapse 1. And that also means that if you have, let's say, matrix multiplication, which has 3 nested loops, you may be able to collapse those into an n cube space, right? IJK, that's the nesting of a matrix multiplication. So you can use collapse 3 there, and there might be other codes which you might want to collapse. However, you have to be a little careful about this part. So in this case, for I and for j are just immediately following each other. There is no statement in between, right? Which may not be the case always, in which case you might not be able to collapse, or you have to modify your loop such that these come adjacent to each other, right? So if these are directly nested within each other, then you will be able to collapse them. Otherwise, the compiler will not be able to do that. All right. So yeah, so that is what I wanted to highlight. Okay, one of the important parts. So this part is okay. You can parallelize a loop, and if you have nested loop, you can use collapse and so on. And by the way, I forgot to mention, it's not always necessary that by collapsing the loops, you will always get better performance. That will depend upon the kind of block you have inside that for loop, whether you have, let's say, large amount of parallelism, or there is some sort of dependence across iterations and so on. So those aspects the programmer has to worry about. But since this is very easy to check, I mean, you just use collapse 1 or collapse 2 and just check what is the performance you are getting for your codes. In general, it is all right to check these two. But yeah, in general, the performance of collapse might get affected by the body of the loop, right? So that you should be aware of. Okay. In general, when we are talking about GPUs or accelerators, we usually say that larger the number of threads, better is the parallelism because you have enough work to be done. So if you have really nicely data parallel operations, there is no harm in going for collapse 2 or collapse even 3, assuming that the data sizes are reasonable. Okay. So do try that out. Okay, so one aspect that I was mentioning here is the loop carried dependence. Does anybody know what that loop carries dependence means? Even if you don't know, it's okay, but just check it. Okay, so loop carried dependence essentially means that there is some write happening in an iteration and the same value is getting read in another iteration. I'll repeat that. There is some memory location to which you are writing in one iteration of that loop, and in some other iteration of the same loop, you are reading from that memory location. Right? In some sense, there is a data race that is happening between across iterations. And therefore, if I want to parallelize these iterations, I am going to be in trouble. If I want to parallelize a loop containing loop carried dependence, then likely that I will be in trouble because when I run them sequentially, if I write in, let's say, 5th iteration and I read in 10th iteration, when I run them sequentially, it works fine. But when I try to run these in parallel, 5th iteration and 10th iteration are actually running in parallel, and therefore it's not guaranteed that the read will follow the write, which is what the sequential semantics expects. And therefore, we have to be careful with respect to parallel execution when you have loop carried dependence. When there is no loop carried dependence, then that means that your iterations are nicely parallel or they are independent. And that is very, very useful from the perspective of parallelization, which is what happens in many cases. But when it doesn't happen, you have to be very, very careful with respect to this. And the reason I'm saying very, very careful is because it can affect your correctness. Like we saw in the context of kernels, that if you do an asynchronous processing, then some printf might just go up, right? I mean, I gave the example of printf, but it could be any arbitrary code which can just happen before the other code. So you have to be a little careful with respect to these effects. And loop carry dependence is definitely one aspect where the compiler can generate an incorrect code. Compiler can generate an incorrect parallel code if you have loop carried dependence. That means you have a data race in your program and you are still asking the compiler to parallelize. It's your bad. Right? Compiler will blame it onto you that why did you ask me to parallelize when you know that there is a loop carried dependence. So it is the onus is onto the programmer. Okay, so let's look at a specific example. So let's say that I specify hash pragma SEC serial loop. What does serial loop do? It executes it sequentially. Where? On the accelerator. This should be understood. Serial doesn't always mean CPU. This pragma means that it is going to run it on the accelerator. Serial means that it's going to run it sequentially. What does the, I mean, let's say I compile it using our PGCC, I get some sort of output, and you can notice line 11 hash pragma SEC for sequential. So it is generating Tesla code. That means it is running on an accelerator, going to run on an accelerator, and it is going to run sequential. So this part is okay. What is the output of this code? Right. Output meaning what is the value that the array contains at the end of this execution. Okay, Swapnil says all 23. Any other suggestions? Okay, I request everybody to try out. Okay, Himanshu says same answer. Jash also says same answer. Rajane says same. Yashpal says not no. Okay. So by not known, you mean we cannot deduce it or you don't know it? Yashpal says n value. Oh, I see. Yeah, assume that n value. Okay. Okay, yeah, assume that n is somewhat reasonable. You are right. So n could be an arbitrary value, but yeah, let's assume some positive value for n. Okay, so we'll go with your suggestions that it should contain all 23 as the arrays, right? So array is going to be initialized with 23 comma 0 0 0 n elements, n minus 1 zeros preceded by 23, and this starts from 1. I loop starts from 1, so a of 1 equal to a of 0. So a of 1 becomes 23, then a of 2 becomes 23, and so on, right? So that is the sequential execution of this code. This all seems to be fine. Okay. Now, yeah, so this is what happens. Now let's change the, yeah, one thing to observe is this loop carry dependence. So ith iteration is dependent on I minus 1th iteration, right? So there's a loop carry dependence across iterations. So we have to be careful about that, and kernels was in some sense intelligent, but it also could cause some surprises, right? So in a similar manner, in this case also we have to be a little careful. Okay. Now let's add this parallel loop. Now what is the output that you think will this program give? And does this, okay, so I'll just show the output, but yeah, it turns out to be a wrong output. And maybe the thread, I mean, the first thread probably did the work correctly, whereas the others borrowed the old values, right? So the old values were all zeros. So iteration number 1, that is I equal to 1, that copied 23 and all others copied 0, and then they all wrote it, right? So in parallel. And therefore it turned out that we are getting this particular output on the GPU. There is also some sort of a SIMD execution happening, because of which such an output you can get. But definitely this is wrong. Why do we say wrong? What is the meaning of wrong here? Wrong is different from the sequential output. Sequential output is our golden output. That means that it has to be, if I don't have any parallelism, then whatever output I get sequentially, that should be the output that I should get out of that same program, assuming that the semantics are satisfied. In some cases, we are okay with some change in the output. For example, the printfs might get jumbled, right? So we are okay with that. So subject to that, the output should match the sequential execution. Okay, so we get this wrong output. I hope everybody is able to see why we can get a wrong output. It's also possible that you might get a few 23s and then zeros. That is also okay. And it's also possible that you will see all 23s. The correct output is also possible. It so happens that that doesn't give any guarantee that your program is correct. As we know, program execution can tell you presence of a bug, but it cannot tell you absence of a bug. A program execution can tell you presence of a bug, but it cannot tell you absence of a bug. Oh, I ran the code 10 times and it gave the correct answer. That doesn't mean that the program is correct. Maybe we are lucky 10 times. That is also possible, right, in the theoretical sense. All right, so we have to fix this, and we cannot afford to do this. But the main takeaway from this slide is that if you have arbitrary loops, parallel hash pragma ICC parallel loop can create trouble with respect to correctness, and you have to be careful, right? So the compiler might just go ahead with the parallelization, and it might not give you any information with respect to that there is a loop carry dependence and so on if you just use this. Okay. And you have to be careful. The compiler definitely has ability to check these dependencies, because that is what it did when we were looking at the kernel's construct. It checked that A of 9 was getting used, so it generated a construct, generated a kernel corresponding to that single printf, and it executed it on the GPU, right? So it was able to figure out that there is a dependence, right? Let's make use of that facility which the compiler has, right? How do we do that? I'll show you now. Okay, so this particular loop, when we by default say that ACC parallel loop, that means that we are specifying that the loops are independent, the iterations are independent. There is no loop carry dependence, and therefore there is an independent clause which you can also specify, which is the default, right? In this case, when you do not want this to be the default, when you want the compiler to go figure out, spend some time identifying if there is loop carry dependence, then we have to specify this auto keyword. This clause tells the compiler that don't assume everything independent, go figure out the dependencies, and if there is loop carry dependence, be careful. It is alright not to parallelize this, run it sequentially on the GPU, but do not give me incorrect code. So that is what this auto keyword is, and that is very useful. By the way, auto keyword can also give you that if the program is, if the iterations are independent, then run this code in parallel. And therefore, auto is going to be kind of your savior in this case. So learn to use auto as much as possible. Instead of just doing hash prime ICC parallel loop, do hash prime ICC parallel loop auto. That is going to be useful. If you are fully sure that, okay, this loop is not going to be having any dependence, then you can reduce some of the compiler's work. You can reduce compiler time by specifying loop independent. And that is also shown on the output, where the line number 11, the non-boldface line number 11 says hash pragma ICC loop sequential, and that is what we want. And then it is also giving this information: loop carry dependence of A, that is the array A, prevents the parallelization, and there is a backward dependence, right? So the ith loop depends upon I minus 1, ith iteration depends upon I minus 1th iteration, so it's a backward dependence. There could be cases when you will have ith loop is dependent on I plus 1th or I plus kth iteration. That is also, there are codes like this also, that is called as a forward dependence. Okay. Any questions on this one so far? Okay, so I hope that you are able to understand the importance of this auto keyword, and then we actually see the exactly correct output, because anyway it is running sequentially on the GPU. But does that mean that we cannot have any data race in our program? Well, yeah, by default you should not have any data race in your program, but if you have, then you have to tell the compiler that it may have a data race, like by specifying auto, or we have to take care of the synchronization across threads, right? One thread is writing, another thread is reading. There should be some coordination between these two threads. It cannot arbitrarily happen. So think about this, right? So we all teach you on the same board, right, in the physical world, but there is a coordination across us that we use different slots, and therefore we don't come to the board at the same time. So that kind of coordination, if we follow, the faculty members follow, then it's going to be same academic work for the students, right? Otherwise, if two faculty members end up writing onto the same board at the same time, teaching two subjects, well, I leave the rest for your imagination. Okay, so let's move ahead from here. Can we have any data race? Yes, you can have data races in the program, and we'll have constructs that OpenACC supports, which will allow us to handle these data races in a legitimate fashion, in a reasonable fashion, right? So one of such constructs is an atomic instruction, right? So let's look at this program. I define n to be 100, and there is some x global variable or shared variable which I specify, not global in the C sense, but global meaning that it is shared across all the threads. Then I have this parallel loop which goes over I equal to 0 to n, a of I equal to I as before, but now there is an opening parenthesis, and therefore I have additional statement x plus equal to a of I. As far as a of I equal to I is concerned, that is nicely independent computation across different iterations, but x plus equal to a of I, which we have seen earlier as sum plus equal to a of I, for example, is has a loop carried dependence, right? Where does it come from? Well, I am writing in ith iteration, but I am also reading the value of x, which is coming from the previous iteration. Right? In the sequential setting, this is x equal to the previous value of x plus a of I. Right? In the next iteration, this is going to be whatever is the previous iteration's value x plus equal to, the new x value plus equal to previous value of x plus a of I plus 1, and so on. So there is a loop carry dependence, and this is a backward loop carry dependence. So one of the ways in which this can be fixed is if we specify auto here, that is going to just sequentialize this iteration, this loop. That means that the whole loop is going to run sequentially on the GPU. But what I understand by looking at this code as a programmer is that yes, there is a sequentiality involved in terms of x plus equal to a of I. I would like that to be executed sequentially, but a of I equal to I is nicely parallel. So I would like that to be executed in parallel. Okay. So one of the ways in which this can be done is that I have two loops. One for loop just does a of I equal to I, and that I parallelize as independent. And then I have another for loop, which I say hash pragma ACC parallel auto or sequential, and that executes sequentially with x plus equal to a of I. That is also fine, but that one of the more productive ways of doing this is to have combined these loops, because the logical semantics of the program are better conveyed if we, let's say, combine these two loops. And that's why sequentially we had written x plus equal to a of I in the same physical block as a of I equal to I. And therefore we would like to actually maintain that. One way of specifying that is to specify something called as an atomic instruction. What does that mean? Does anybody know the meaning of atomic instruction? Or an atomic block of code? So it means run to completion without context switching. Yeah, to some extent, but not the exact. It's actually, in case of atomic, there is a possibility of context switch happening, but yeah, that's why I want a little more precise. I understand what you are saying, but a little more precise.
Is it something like if it is going to happen, it will happen totally, or it will roll back?
Okay. So in case of operating systems, yeah, so actually maybe we are talking from the database transactions perspective where that rollback is coming into picture. But yeah, the rollback doesn't happen here, thankfully. What Josh has said is what happens, that the instruction or the block of code is going to execute completely or not at all. Now, completely seems understandable, but what is not at all? So we say in some sense the block of code or the instruction is atomic if it executes completely or not at all. What does that mean? Okay, so it's not that it doesn't run at all. What it means is that you as other thread, you as other concurrently executing thread are not allowed to see any update which is in between these two states. So either you will see the value that is being written to x as the previous value before this atomic instruction is executed, or after the atomic instruction is over and nothing in between. Right? So Just to give you an example, if I am looking at, let's say, a bus which is going from, let's say, one stop to another, and it is going via a certain route. If I am allowed to probe only at the source and the destination, then I cannot know what happens in between. Right? So maybe there is a tunnel, and that tunnel doesn't allow me to see through how many passengers are there, whether somebody is getting down inside the tunnel, whether somebody is getting up inside that bus from the tunnel, etc. Because I am viewing it, let's say, via my this chopper or helicopter or some such aerial view. So what I can see is what happens just before the tunnel, or what happens at the end of the tunnel, or what happens at the source or the destination, but nothing in between. I cannot know what is all happening in between. Think about these as library functions also. Another example is library functions. I don't have the source code of library functions. Let's say string compare. What I know is what happens when I send the parameters to string compare, and what I know is the final output of string compare. But I don't know what is happening in between. Right? So in some sense, that is atomic from your perspective. So in this context of parallelization, we say that the effect of that instruction is known to other threads, either none or fully, but nothing in between. Contrast it with what happens when you do not have atomic. Right? That will give you an answer. In that sense, your tunnel is transparent. It's made of a glass, and therefore I'll be able to see who is getting down, who is getting up. Or your function code is available, so I know precisely that these are the instructions that are going to get executed inside string compare. In this case, I'll be able to know that, oh, x plus equal to a of I. So what is happening is that there is load of a of I happening. Then after that, that is getting stored inside a register. After that, that register's value is going to get added with another load, which is the load of x. Once I have this modified value into that register, then that register is getting written to, stored into the memory location for x. If all of this I am able to view as another thread, then the instruction is not atomic. And why is that important? Because of the example that we discussed earlier, where I just have for loop and x plus plus, right? Initial value of x is 0. In this case, x plus equal to a of I. If I do not have this guaranteeing of this atomic instruction, then the value of x, which is supposed to be the sum of all the elements from 0 to n minus 1, may not be guaranteed if I do not have this coordination across threads, if I do not have this synchronization across threads. So atomic is giving some sort of a discipline to the threads, saying that there is some sort of a lock which I am holding, right? Each thread needs to go through that lock. Only one thread can hold that lock at any point in time. Whosoever has the lock can go ahead and execute x plus equal to a of I. So let's say thread 5 gets it first. It executes x plus equal to a of I, and then x value becomes 5. Then thread 2 gets the lock. Then thread 5 unlocks it. Then thread 2 gets the lock. It does x plus equal to 2. So x value becomes 7, and so on. Then different threads go on exactly in a similar manner. As far as a of I equal to I is concerned, which is the previous statement, that gets executed in parallel without any guard, because it is writing to different memory locations. So I am fine with it. Okay. So this ACC atomic is a very useful instruction when you have large piece of code which is parallel, but there is a small aspect which is a shared accumulation. Many times this accumulation is likely to be in some sort of, in your simulation codes, there is going to be some sort of a diff which you will create, right? So some sort of an error that you will create, right? Different threads are doing some things in parallel, and then whatever is the effect, whatever is the computation they are doing, some small effect needs to be accumulated inside a diff. That diff or that error needs to be compared at the end of the parallel execution to be lower than a threshold or upper than a threshold, and depending upon that, you will execute the next iteration or not, right? So in such cases, this is going to be very helpful because the rest of the code is parallel. Only this small computation can be atomic. Because it is asking, does it mean that the atomic section is basically executes mutually exclusively for every thread. The effect is so. The effect is so that it gets executed in mutually exclusive manner. The implementation can vary. So the implementation can actually may not do it in a mutually exclusive manner, but the effect is that way. So think about it this way: that how should I say? Okay, so let's say that I have this, I go back to my example of the function calls, or maybe the tunnel, right? Uh, if I know that there is nobody who is watching, right? So there is no drone which is watching from above, I can as well not have the tunnel. And still I'll be able to ensure that the instructions, the execution is almost atomic, in the sense that there is nobody who is really peeping into what is happening inside the tunnel. So I'm just giving one example, but what that means is that your implementation might take advantage of that there are, because of the situations, you may not exactly execute it in a mutually exclusive manner, although that is usually the case, but that need not always be the case, right? So mutual exclusion essentially means that when one thread is executing, the other thread cannot execute at all, right? That particular block of code, that is a mutual exclusion. That need not always be satisfied. Under optimized executions of these atomics, you can execute them in a non-mutually exclusive manner. And the reason being that not all threads are reaching this instruction at the same time. In case of accelerator-based codes, let's say some vector is, some warp is executing this x plus equal to a of I, right? But there may be another warp which is still executing a of I equal to I. I don't need to protect these two warps from each other. Right? I do require mutual exclusion within the warp, but not across the warp. So that is the reason why it may not, as an optimized implementation, it might do away with this mutual exclusion, but mutual exclusion is going to guarantee you atomic execution. Okay, but it does something more than what is required. Just says yes, that is what happens. Whatever is written inside the atomic acts as a critical section. Yeah, so in general, that is what is the default.
But,
yeah. Sorry, go ahead.
Sometimes sometimes data arrays might not be harmful. So,
Yes,
so atomics might be optimized for that, for benign data arrays.
Yeah, sure. Thanks. Rajendra says, so if A of 5 has been written, x plus equal to A of 5 will take place. Otherwise, it will wait. Yes, in some sense, that is going to wait, but these are not blocking, right? So it will wait. So the way it gets implemented, I'll tell you what happens at the hardware level, right? So typically these atomic instructions require support from the hardware. The way hardware is going to do is that they are going to maintain a small buffer, a write buffer, in which these writes are going to go. So the different threads might enqueue into this buffer their writes for the same memory location at different times, and until one of them is over, the second is not taken for execution. So there is this buffer is empty like a queue, very similar to our command queue, and therefore that atomic instructions are guaranteed to see one of those writes, right, in some arbitrary order. If it is a relative update, then it's all right that every effect is going to get accumulated in that memory location. When you do not have atomic instructions, it's possible that this buffer might not get, there is a write buffer, but not the way this emptying sequentially may not get done. And therefore, it's possible that you might be able to read and write that memory at arbitrary location, at arbitrary places in your code. And that is what can cause what Swapnil was suggesting as a context switch, right? So you are executing this instruction halfway, and then there is a context switch, which means that some other thread sees the value, peeps inside the tunnel, and then sees that there is some intermediate effect happening, right? So that is what it means. Okay, so yeah, but you can view this as a critical section. The reason why I was saying that this is not blocking is that there is a bounded wait that is going to happen. it doesn't block indefinitely. Unlike our lock-based codes, although I gave the example that there is a lock, then the thread executes and then unlocks. So unlike our lock-based codes where the thread can actually block and block indefinitely, there is a bounded wait in the context of these atomic instructions. Why? Because the number of threads is limited. In this case, let's say n threads are there in the worst case. The maximum amount of time that a thread needs to wait is going to be proportional to this n. And each thread is going to execute this instruction in limited amount of time, that is x plus equal to a of I is going to get executed in finite amount of time, and therefore there is a bounded wait when it comes to atomic instructions. In case of locks, the code can be arbitrary. You can have a while loop inside that lock-unlock code, which is not possible for atomics, right? In OpenACC. In fact, you cannot write more than a few lines which are atomic in nature, right? There are only a few functions. For example, plus equal to, minus equal to, etc. These are very few items which are supported as atomic instructions in the context of OpenACC. Right, so there is a wait at the write buffer, but this wait is bounded, and that makes atomics different from the locks. In fact, atomics are used to implement locks. Atomics are used to implement locks. So let's remember that. Those of you who have probably studied operating systems will be able to see the connection. We used to have this CAS instruction, right? Compare and swap. Then we have this test and set instruction. These are all primitive instructions similar to these atomics. These get used to implement the lock implementation, or P and V operations, or wait and release operations, and so on. Okay. Yeah, those of you who don't know about these operating system concepts, ignore that. That's not really important. But the important takeaway here is that if you have a data race inside your program, you can guard it using atomic, not always, but in some cases, right? Like in case of plus equal to. All right, any further questions? Ashwati is asking, what if there was a data carried dependence? Will a thread wait until the dependence is fulfilled? Data carried, loop carried dependence, will the thread wait until the dependence is fulfilled? No. The thread is not going to wait for that data to be available. So for example, if I have a loop which is like a of I equal to, or x plus equal to a of I minus 1, something like that, will it wait for I minus 1 being written by the previous thread? So let me state this in a little different way, right? So I'll answer Ashwati's question in a different way. Currently, a of I is being written to in ith iteration, and a of I is also read in ith iteration, right? So this is what the code is doing. One before the atomic pragma, one after the atomic pragma. But the same memory location is being written to and read. What if I am writing to a of I, so the first instruction is a of I equal to I, but the second one is x plus equal to a of I minus 1. And let's say I goes from 1 to n. Will it make sure that a of I minus 1 is written in I minus 1 iteration, and then the ith iteration is going to execute? No. This means that there is a data race across these two statements. Currently, the data race is only with respect to the reading and writing of x in this statement, right? X plus equal to a of I, which we are guarding using atomic. But if I am writing to a of I and reading from a of I minus 1, the data race exists between a of I minus 1 of another thread, that is I minus 1 a thread, and the thread I which is reading that value. Can I not apply hash pragma ACC atomic to these two statements together? That is where the constraints come into picture. So you are right that if there was a way to make this whole code atomic, then maybe it would have served the purpose, but that would have also sequentialized the processing, but that's a separate issue. But yes, at least the code would have been correct. Unfortunately, in case of OpenACC, these atomic instructions are very, very limited. So plus equal to, minus equal to, or equal to, and equal to. These are a few examples to which you can apply this. You cannot apply it to more than one lines of code, and therefore we won't be able to apply it. So is by default this thread going to wait? No, the thread is not going to wait. So if I have a of I equal to I, then there is a pragma ACC atomic and x plus equal to a of I minus 1. I might read the previous value of I, or I might read the modified value of I. Either way is possible. So there is a data race and I am not taking care of it, and therefore my code can misbehave. Okay. Any other concerns, questions? All right, that was a good discussion. Let me move ahead from here. So atomics, certain instructions can be marked atomic. It's useful for coordination across threads, and only a few such operations are supported. That is what we discussed. But there is something better than atomic which you might be able to do. Atomics are usually a little faster, but there is a little generalization of this. Not really generalization, but there is something which covers more space than atomics, and that is called as a reduction. So that is what we are going to study now. Okay. So reduction essentially means that you are given input as a set of values, and the output is a smaller set of values, typically 1. And that means that the n set of values, n values, I am reducing to a single value. For this to happen, or for this reduction to apply, the computation must be reducible. What that means is, and this is a recursive definition, that for applying reduction, the computation should be reducible, but I'll explain what that means. That means that the associativity property should be satisfied. Where is this associativity property coming from? This is from discrete mathematics. Those of you who don't know, that is okay. But essentially it means that if I am applying a function, in this case I am specifying that function as a dot operator, this dot is not necessarily multiplication or some other function. It's an arbitrary function. So if a dot b dot c is same as a dot b followed by dot c, which means that the order in which I execute this operation, if it is not dependent on, if it doesn't affect the output, that is, the order doesn't affect the output, that is irrespective of whether I do b dot c first or irrespective of whether I do a dot b first, I get exactly the same output, then we say that dot is associative. As an example, if I have a plus b plus c, whether I do b plus c first and then a plus whatever is the output, or I do a plus b first followed by whatever is the output that I add c to, I get the same value. Well, in this case, we will have to assume that there is no overflow happening, and or even underflow, because ABC could be negative and so on. As long as that is satisfied, I say that plus is an associative operator. Same is the case with multiplication. Right? How about minus? Is minus associative? Okay, is minus associative? Okay, Just says no, Himanshu says no, Subros says no. Why is that? I mean, I can just do b minus c first and then a minus of that. Or I can do a minus b first and from there I avoid minus, right? Just says it must at least be a semi-group. Yeah, that is a very theoretically accurate and correct answer. But I gave you one example, right? So I can do, let me just write it. Isn't this the case? That a minus b minus c equal to a minus of b minus c. I mean, I can do it in any order, right? Then where is the problem with respect to associativity? Abhishek also agrees with me. Okay, So the problem is that I have written that expression definitely in a wrong manner. The meaning of a minus b minus c, the second expression, yeah, so as Josh has given an example, but I can say that a minus b minus c is actually a minus b plus c, right? So the right hand side expression is a minus b plus c and not a minus uh, whatever, b minus c. And therefore, I cannot apply associativity to the minus operation. That is, minus operation is not associative, and same is true with division also. Okay, so that sounds good. But there could be higher level functions. Sometimes I can have an arbitrary set of expressions which might be arbitrary functions which might be cast as a reduction, and I can just say whether associative or not. For example, let's say I am finding maximum element in an array. Right? Maximum element in an array. Can I say that the maximum, finding maximum is associative? In this case, for example, if there are three elements A, B, C, can I say that max of, okay, let me just write that, max of this is same as max of yeah, I'll just write it here. So first I compute the max of AB, and then whatever is the max, to that I apply max along with C. That is one way. Other way is that I'm going to find the max between BC and then A comma whatever is the result. To that I'm going to apply max. So can I say that it is associative? Rajanya says yes, Subro says yes. Ashwati also says yes. Okay. So max is an associative operation. Himanshu also agrees. Yes, so it is an associative operation. So in general, you can have a very arbitrary computation, arbitrary function, which may be cast as a reduction. If it is associative, then we'll be able to convert it into a reduction. Okay. So let's understand what reduction means. So min, max, sum, XOR, many of these operations are actually reducible. These are all associative operators. Sometimes some of these operations can also be implemented using atomics as long as the hardware supports atomic instruction corresponding to this. For example, I can say that if I find atomically the max of AB and apply it to atomically to C, then that is equivalent to applying atomically BC max and then applying it to A, another atomically, and so on. So it can be implemented using atomics, but it can also be implemented in a different way. So for example, atomic addition, atomic minimum, the same way as I was writing, in a similar manner, you can use atomics to perform reductions, but it also adds sequentiality to the execution. There are better ways which are slightly better parallel than using atomics, because atomics are going to add sequentiality. We talked about the write buffer. So that is going to add sequentiality to your writes. So to avoid that, there is a nice hierarchical computation which you can do, which is essentially referred to as a reduction. Okay, so let's understand that within the context of one specific example, where the operation that I'm specifying is the sum operation. I want to add some numbers, right? So I'm specifying these 8 numbers, which is the input, right? In general, there could be n numbers. What I do is, I take, so the way atomics are going to work is that it will take 4, let's say it will take 0, which is the sum, and it will add 4 to it atomically. Then it will take 3, and it will add 3 to that sum. Then 9 to whatever was the sum, which is going to be 7, and so on. So there is a cumulative sum which it will create, but it will not happen exactly in the same manner because different threads are executing in different orders. So it's possible that from 0, I might go to 7, and then I might go to 9, then 2, and so on. So it can happen in any arbitrary order using atomics. What I do instead is that I say that, okay, there are these n numbers, in this case 8, I'm going to take 2 of them and sum them up. So 4 and 3 I sum to 7, which is written below that. Then I take the other pair, 9 and 3, and I sum them up as 12. 5 and 7, 12, and 3 and 2 also as 5. Is this possible to be done in parallel? Yes, if there are n numbers, n by 2 threads can execute these n by 2 sums in parallel. Okay, how many results I get? I get n by 2 results. What do I do with n by 2 results? 7, 12, 12, 5. I can repeat that. So now I have n by 2 sums. I am going to repeat this with n by 4 threads. N by 4 threads are going to give me n by 4 values, 19 and 17, and which I am going to again make use of in the next step and sum them up further. Finally, I am going to get a single value, which is going to be, in this case, 36, which is the actual result I want by summing all of these. So as you can see that there is some parallelism across this, and there is some sequentiality also. So where is the sequentiality here? And what is the length of the sequentiality? Where is the sequentiality in this reduction that I showed? And where is what is the length of that sequentiality? Okay, Jash has suggested that there are log n steps required, right? So since I am taking 2 elements at a time, from n I am going to n by 2, from n by 2 I am going to n by 4, n by 8, and so on. So in the worst case, I can reach 1 in log n steps. And therefore, this sequentiality is going to be vertical. Number of such steps I require is log n, and that is going to add some sequentiality, but there is some parallelism also, which is horizontal, right? So each of these, so what are these different steps? There is some requirement with respect to these steps, right? So what is that? Can somebody suggest? But I hope you agree that there is some parallelism. Although it looks like sum plus equal to a of I is very nicely sequential, because there is dependence of a of I onto the previous value of sum, and therefore this is nicely sequential loop. But with reduction, we will be able to parallelize even this seemingly sequential loop. Okay, the constraint here, and this is shown as these steps, is that the second step should not start before the first, the second level or the second step should not start before the previous one is over. For example, I should not start summing up the values to 19 until 7 and 12 actually get written, right? And therefore, each of these steps need to be separated by something called as a right. Josh, maybe you can let others answer. You know many of these things, but yeah, so this needs to be separated by barrier. Yeah, no problem. Of course, you can ask questions and answer also, but let others also think. That's what I was referring to. Yeah, so these need to be separated by barriers, and you need log in such barriers, log in such steps, right? So this is a nicely hierarchical reduction, right? This is called hierarchical because you have this hierarchy of different steps, n by 2, n by 4, and so on. Okay. Any questions on this reduction? I have not yet specified how do you specify this in OpenACC, but I wanted you to think about first how that might be internally implemented in parallel. Because reduction is something which many people are aware of. They have heard of, but they may not know exactly what is happening. That's why I spent some time on it. Okay, just a deviation from OpenACC to CUDA for a minute, because we won't be able to implement this in OpenACC. So in case of CUDA, this particular piece of code that I'm showing gets executed by different threads. In this case, we said that there are n numbers and n by 2 threads can operate in parallel. So think about it this way, that there are n threads available and only some of them are going to act on it. Right? So in the first iteration, n by 2 threads should execute, then n by 4, and so on. And therefore, the loop count goes from n by 2 all the way to 1, and then when it becomes 0, that is 1 by 2 happens, then we come out of this loop, and every time I reduce the number of threads to half. If my thread ID, ignore the syntax as such, but you should know that this is some thread ID. If my thread ID is less than this of, that is in the first iteration 0 to n minus 0 to n by 2 minus 1, in the second iteration 0 to n by 4 minus 1, n by 8 minus 1, and so on, then I perform some operation. What is the operation that I perform? A of thread ID x dot x, that is A of my thread ID, plus equal to A of thread ID plus of. A of thread ID plus of. This is not exactly what I have specified. It's not adding up consecutive elements. What it is adding are 4 and 5, 3 and 7, 9 and 3, and 3 and 2. Right? So that is what it is doing, as I can show you pictorially here. So in the first iteration, and I'm writing it to the same array, right? So original input array contains these 8 numbers. After the first iteration, I have 4 plus 5 written at wherever 4 is, 3 plus 7 written wherever 3 is, and so on. These values remain the same. These are not written to because there are only n by 2 threads which are writing. And sync threads is some sort of a barrier. Right? After every iteration, I need a barrier. And then these n by 4, n by 2 get combined into n by 2. So 9 and 12 sum up, and then 10 and 5 sum up and written here. Finally, the array of 0 gives me the final answer. Okay. Any questions on, I mean, don't worry about the CUDA reduction code, but I wanted you to understand how that might get done on the GPU. Any questions so far? Okay, so I'm going to go ahead from here. In general, this code works for only powers of 2, but you can get it working for arbitrary values of n by doing some small checks here and there. Okay. Because as you know that even if you have 9 numbers here, as long as you have 5 threads, you'll be able to do the processing. That 5, I mean that 9 values will get converted into 5. From 5 you will come to 3. From 3 you will come to 2. From 2 you will come to 1, and so on. So you can get that working reduction. Yeah, so you can do the reduction in other ways also. For example, instead of combining 5 and 4 and 5, I can combine 4 and 2, 3 and 3, 9 and 7, 3 and 5. That is another way. In which case, the access function will change, but I can as well implement it in different ways. Anyway, ignore that for now. But this was just to convey to you how it can be written. Okay, so let's come to the OpenACC world. How do I specify that I want to do this reduction and I want this coordination to be automatically taken care of? I am not going to write all this A of thread ID x dot x plus equal to A of 2 into thread ID x dot x and minus 1, etc. All of that I am not going to do. Right? Finally, OpenACC says that more science and less programming. Right? So I am not interested in writing this code. So the syntax of reduction in OpenACC is very similar to that in OpenMP, and it just specifies that whenever you have a parallel loop, you can specify a reduction there, which says that what is the operator that should be used and what left-hand side variables that reduction should be applied to. Okay. In this case, it so happens that both x and y are undergoing plus equal to, that is the sum is getting accumulated, and therefore I can specify plus colon x comma y. Alternatively, if this would have been x plus equal to 1, y star equal to 2, I could have specified plus reduction plus comma x and then reduction star colon y, right? So, and as far as a of I equal to I is concerned, that is the third line, that is nicely parallel. There is no reduction really required there. Okay. So what is the output of this code? Assuming that n is let's say 99 or n is 100. So assuming n is 100, what is the output of this code? Okay, maybe it's a long time since the class has started. 100 and 200, right? So x should be summed 100 number of times, so it should be 100, and y is getting summed also 100 number of times, but 2 at a time, and therefore it should be 100 comma 200. As Rajanya has pointed out, yeah, Himanshu, 100 is correct for x, but for y it will be 200. Okay, so yeah, and the compiler also tells you that. The compiler says that I'm generating this reduction for y and x. It has taken for some reason opposite order, but doesn't matter. And it gives you the correct output as x equal to 100, y equal to 200. Okay. There are multiple reduction forms which get supported. For example, we talked about x plus equal to 1. But you can as well specify x equal to x plus 1 and still the code will work, right? Then you can specify 1 plus x on the right hand side. You can have plus plus x, x plus plus. All of these forms work with OpenACC, and that's kind of a syntactic sugar or additional processing which helps us. Otherwise, you will get surprises. If only plus equal to is supported, then I might write the code as x equal to x plus 1, and maybe it will not do a reduction. Right? You will lose on performance. Although correctness wise, it won't be a problem. You might lose on performance. That doesn't happen. Thankfully, the code works even if there is arbitrary different ways in which you do it. Okay. Okay, so what will be the output of this particular program? Quickly, let me see who all can answer this. Okay, Rajanya says n into n minus 1 by 2. Okay, where n is 100. Okay. Anyone else? Okay, so those of you who were able to do but could not, okay, 4951, okay. Ashwati says n into n minus 1 by 2 plus 1 as sum is initialized with 1. Okay. Good. All right. So thanks for these answers, Swapnil, Ashwati, and Rajanya. Well, as I was saying earlier, doesn't matter if the answer is incorrect, but very important, or even if you don't mention it in the chat, it is all right, as long as you have tried it. Okay. So that seems to be, okay, sorry. That seems to be correct, that it should be 4951 because we are starting with 1 rather than 0. Actually, yeah, that seems to be correct because a of I is nicely parallelized. A of I equal to I is nicely parallelized, the first loop. So that happens. The values are 0, 1, 2, 3, 4. And then this is sum of 99 numbers. Sum of 99 numbers is 99 into 100 by 2, which is going to be 4950, and then plus 1. So it should be 4951 is also what I think. Okay, sounds good. Yeah. Yeah, there are other reductions possible. For example, apart from this plus, you can have a star, max, min, ampersand, or XOR, and then the logical ampersand and logical OR. All of these are supported in C++. And similar manner, all of these are supported in Fortran also. Apart from that, there is this equal to and not equal to, which is also supported in case of Fortran. So for example, as far as max is concerned, you should be able to write the example that we were taking, that max is associative, and therefore I should be able to write a reduction code corresponding to that. But how do I specify max? So max is specified using a max keyword in the clause. Uh, so like we were specifying plus or minus, plus or star, you can specify max or min here. And interestingly, we can write very arbitrary piece of code here. So I am actually writing if a of I greater than x, then x equal to a of I, right? There is a very arbitrary piece of code where I am computing the maximum. That doesn't mean that the compiler is very intelligent here. It just means that the compiler is believing that you are computing a max with that computation. Okay, so if I specify, if I write if a of I greater than x and x equal to a of I and specify reduction min comma x, you might be in trouble. You might get some wrong answer, right? So yeah, as long as you are writing it in the same way, it should be all right. What should be the output of this code, by the way? Someone? Okay, Abhishek says 100, Ashwati says 100, Suro says 99. Good, we have different answers. Okay, now I request others to support either Abhishek, Ashwati or Suro. Let's see which party wins. Himanshu says 99. Rajanya says 99. Okay, 99 is winning. Sandeep is saying 99. Okay, we'll give another chance to Abhishek and Ashwati. Do you want to change your answer, Abhishek, Ashwati? Or any of the 99s want to change your answer to 100? Swapnil says 99, Abhishek says 99, okay, Ashwati says 99. Okay, so all of us are on the same page. It should be 99 because the a of I equal to I initializes from 0 to 90. Okay, sounds good. And then we find the max over this I. So, I mean, there's still a small piece of code, but you can visualize how different parts of the code are going to look like in your program. There might be some initialization, which you parallelize using ACC pragma loop. Then there might be, let's say, a fixed point computation, which might have a do-while loop. Within that, there might be a for loop, which goes over all the particles or all the elements of a matrix or a vector, which you can possibly parallelize in general using parallel loop. But there might be some element which should be private. In this case, X should be shared, so that is not a problem. But maybe I should have some private variables, so I will write hash primacy parallel loop private some XYZ. Then if there is some reduction which is possible, if I don't write reduction, what happens is another thing that you should check. It so happens that in most cases, the compiler will be able to figure out that there is a race and might be able to even generate a reduction if it is in standard form, right? But for these arbitrary computations, it may not be able to figure out that there is a reduction possible, right? Because I can write very arbitrary pieces of code. So thankfully you can also write x equal to, I mean, using question mark colon format instead of if else. That is also okay. But currently the user-defined reductions are not supported in OpenACC because we said that for reduction the only requirement is that it should be associated, and I can have a very arbitrary function which is associated. But currently that is not supported. The reason I am mentioning this is because user-driven functions or user-driven reductions are supported in OpenMP. So we hope that it will get supported in OpenACC in future. Okay, so I'm almost done. Yeah, so today we looked at the loop construct, and within that the basic syntax was just parallel loop, but then within that there were quirks which relate us to the nested loops, which we solved using collapse clause. Then we looked at loop carry dependence and how it can affect correctness. Then to fix it, we used atomic instructions and or atomic clause, but it had a kind of limited syntax. So we looked at a more general form of reductions, which allow us to take care of different kinds of coordinations across threads and how it happens in parallel in a hierarchical manner. So that completes our discussion on the compute constructs. right? So all these parallel kernels and loop are related to computation. But what we have not talked about is the data transfer, which is the topic of our tomorrow's discussion. I'll stop here. If there are any questions, we can take those up now. Sorry about the noise. Our neighbors are enjoying. So. All right. So if there are no questions, I'm going to stop the recording now.